We're going to look at factoring a difference of squares. So we're going to look at a product of a sum of and a difference. So complete the following table by expanding and simplifying or using algebra tiles. Go ahead and pause this and expand. I'm going to just write in the answers here. Okay, so we can see that I showed kind of the full expansion in the first one. We get x squared plus 4x minus 16. So our middle terms here cancel one another out. And they will always do this when we end up with two binomials that have the same values and simply differ by the sign in between. So I'm going to go ahead and answer the questions for 2, 3. How are the binomials in each multiplication alike? Well, I just said that they have the exact same values, coefficients, variables, etc. And they are different only by the sign separating the two. So the sign in the first one is always the same. So 3x and 3x were identical. It's just the sign separating the first and second term. How do the terms in the product compare with the two binomials in each multiplication? What we can see is that the first term in the binomial is squared for the first term here. So x squared is, x to the power of 2 is x squared. The second term is the negative value of 4 squared. So we get negative 16. Again, we could do that here too. We get 3x times 3x is 9x squared. 2y times 2y is 4y squared, and they are separated by a subtraction. Explain why there's only two terms in the product. Well, our middle term, if you will, gets canceled every time. So we have a, in this case, it was a positive 4x and a negative 4x. They are always going to add to 0. So write a rule for finding the product of the sum and difference of two terms. My goodness. What we get is if we have an a plus b times an a minus b, again, just differing by that sign, our answer will be a squared minus b squared. So I have provided a few more examples here. Again, just to highlight that these middle terms always end up canceling in our difference of squares. So what we could write for a general rule here would be a difference of squares has the form a squared minus b squared, where a squared minus b squared is equal to a plus b times a minus b. So you can recognize a difference of squares because both the first term here and the second term here can be square rooted. So a squared, we can actually get a perfect square, and b squared, that second term, is also a perfect square. Okay, so for example, I have one in my notes. Oopsie, that's not what I want to write with. If I have 16x to the power of 4 minus 49y squared, I know that this is a difference of squares because I can square root 16x to the power of 4. That is 4x squared. And I can also square root 49y squared. That is 7y. So I could write the difference of squares for this as 16x to the power of 4 minus 49y squared is equal to 4x squared minus 7y times 4x squared plus 7y. If you FOILed that out, we should get the exact same answer as 16x to the power of 4 minus 49y squared. So using those patterns, go backwards and factor the following difference of squares expressions. So again, I'm always going to end up with two brackets where my terms are separated by a positive and a negative in between, or adding and subtracting. The first term will be the square root of x squared, which is x, and the square root of 36 is 6. So x plus 6 times x minus 6 will equal x squared minus 36. Pause the video and go ahead and try all of these. I'm just going to quickly go ahead and finish them up here. So the square root of 9a squared is 3a, and we're going to get plus 8, and then we're going to repeat that 3a minus 8. Square root of p to the power of 4 is p squared. So we're going to do plus the square root of 121q squared is 11q. And then we're going to repeat that p squared minus 11q. 16 square rooted is 4. So plus 25 square rooted is 5y. And then we're going to multiply that by the same thing with subtraction. This one looks a little bit tricky only because there's a fraction. But we're going to end up with the square root of x squared over 16 is x over 4. So plus the square root of 9 over 49 is 3 over 7. And the square root, again, subtracted. The last one looks tricky here. 2 and 32 are not perfect squares, but they have a greatest common factor of 2. So I'm going to factor out a 2 first and see if that helps. I'm going to be left with x squared minus 16. Now, what's in the brackets here is a difference of squares. So I'm going to get 2, and then I'm going to multiply by x plus 4, x minus 4. Because if I expand this, remember, it will still equal my x squared plus 16. So don't put 2 twice, okay? 2 only belongs once up at the front. So this is starting to blend a little bit of our factoring. So we want to always check for that greatest common factor before we get started, factor it out, and then we can factor what remains into our two binomial statements. A binomial squared, it looks very similar. Instead of a positive and a negative, they're just going to be the same thing multiplied by itself. So what we're going to look at here is it would be x plus 3 times x plus 3. So go ahead and pause this and FOIL all of these examples out. So we should get x squared plus 6x plus 9. Here we're going to get x squared minus 8x plus 16. We're going to get a squared plus 2ab plus b squared. I had one more in my notes here. It's missing. I had a minus b squared, and we're going to get a squared minus 2ab plus b squared. So, what do we notice in the first term of each trinomial with the first term in each binomial? In the trinomial, the first term is the first term here squared. Okay. What do we notice about the last term? Well, 9 is the second term in our binomial squared. What we get for the second term, or the middle term in each trinomial, is the first term times the second term, so 3x times 2. Okay, so let's try that again here. The first term times the second term, so negative 4x times 2 is negative 8x, which was our middle term here. So we can recognize our binomial squared with those three things. First term is the first term in our binomial squared. Second term is each term in the binomial multiplied by one another times 2. The third term in our trinomial is the last term in our binomial squared. So we can write a rule here for squaring a binomial. We can say that a binomial, a plus b all squared, is equal to a squared plus 2ab plus b squared, or a minus b is equal to a squared minus 2ab plus b squared. Again, just because of our b was negative in this case. So a perfect square trinomial results from squaring a binomial, so raising it to the power of 2. Perfect square trinomials can be factored using the patterns we just talked about. In a perfect square trinomial, the following conditions are met. The first and last terms are perfect squares, and the middle term is twice the product of the square roots of the first and last terms, aka it's the first and the second term multiplied by themselves times 2. So we're going to explain whether or not these are perfect square trinomials, and if they are, we're going to factor them. So our middle term here is not going to work, okay? Because technically I should have had x plus 3 squared to get our 9 and x if these were a perfect square trinomial. This middle term, if this was our square, should have been 3x times 2, which would have been 6x. However, we ended up with 7x. So this is not a perfect square trinomial. Okay. In our second one, we see a 25 and a y squared, which are perfect squares. So I could write this as y and 5 times y and 5. Now we need to decide if it would be a positive or a negative. Now looking at our middle term, it's a negative. And remember, this was 2 times the first and the last term. So if we ended up with a negative, this actually needs to be a negative 5. They're both going to be negative 5s because a negative 5 and a negative 5 make our positive 25 still. So does this work? Well, 2 times our terms multiplied together. So 2 times y times negative 5 is negative 10y, which is our middle term. So yes, this is a perfect square trinomial. Okay, our third one here. We're going to use the square root of our first term. So 9a squared is a perfect square. So we will use 3a. And our last term, 4b squared, is a perfect squared. So we'll use 2b. So 3a and 2b. Again, based on what we just did here, let's use the sign in our middle to decide if it's a positive or a negative. Because this is a positive, we will have positives between these two. So does this work out? 2 times our first term, 3a, times our second term, 2b, is equal to 2 times 3 is 6, times 2 again is 12ab. That is our middle term. Therefore, yes, this is a perfect square trinomial. Last one here, square root of 49 is 7, and the square root of x squared is x. So I'm going to use both of those. The middle term is positive, therefore these are separated by addition. And so double checking that middle term, 2 times our first term times our last term, 2 times 7 times x is positive 14x. Therefore, our middle term works, and yes, this is a perfect square trinomial. The last task here, or it could be our exit task, verify that this is a perfect square trinomial and then factor it. Again, the first and the last terms need to be perfect squares. So the square root of 49x squared is 7x. The square root of 4 is 2. The middle term is 2 times the square root of 49x squared, which was 7x, times the square root of 4, which was 2, and that would be 28x. Now remember, we can have this as a positive or a negative 2, so this will work out to be our negative 28x. If you're not sure about that positive negative thing, remember 2 times 2 is 4. Negative 2 times negative 2 is 4. So the square root of 4 could technically be a positive or a negative 2. We could also see that once we verified that these numbers are correct, we can go ahead and put their signs in. So 7x and 2, 7x and 2. These will be separated by subtraction because our middle term is a negative. If you went and FOILed this out, so 7x times 7x times negative 2. So 7x is, 49x squared minus 14x minus 14x plus 4. So we end up with 49x squared minus 28x plus 4. That is exactly the same as what we got to start with.